I'm very happy to introduce Liane Gabora, who's one of our colleagues from the Okanagan campus of UBC. She was actually in the first cohort when UBC Okanagan joined the UBC family, as it were. So she's been there for about 16 years, she tells me. She is not a physicist. She's in a psychology department, but she's done an extraordinarily wide range of interdisciplinary research and published in many different fields. So she has applied a lot of, hard science ideas to psychology, and included in among that is thinking about how to use the sort of mathematics of quantum mechanics as a way of modeling decision-making processes and humor and some other things in cognitive sciences, and that's what she's going to talk to us about today. So take it away, Liane, it's all yours.
Thank you, Douglas, and thank you for the invitation. I'm thrilled to be here presenting this to you. So I would like to start by giving you an overview of what I'll talk about. So I'll tell you a little bit about the rationale for applying quantum mechanics to cognition. It seems like a strange thing to do, so why would we even want to do this? And then I'll give you an example from concept combination, and an example from humor studies, and a preliminary study that applies this mathematical formalisms from quantum mechanics to humor. And as Douglas was saying, humor is not the main thrust of what I do. It's somewhat peripheral to the main body of research carried out in my lab. So what I work on primarily is, it all started with trying to understand in what sense culture is an evolutionary process. So how does culture evolve? Developing a theoretical framework for cultural evolution in the sense of cumulative, adaptive, open-ended cultural change. And that leads to trying to understand how cumulative cultural evolution actually started evolving. How did humans develop the capacity for cumulatively adapting ideas, each person putting their own spin on the ideas that came before? And this involves collaboration with anthropologists and neuroscientists and archaeologists, and applying things like autocatalytic networks. And then that leads to, how do we understand the processes that fuel cultural evolution? So how do we understand creativity? And since concept combination lies at the heart of the creative process, it seemed like a manageable way to address something as vast and elusive as creativity. So creativity boils down to putting together two things that haven't been put together before, or seeing something in a new context. And it turned out that studying how concepts combine is a vast topic, and it led me down the rabbit hole that leads me to be giving this talk to you today. So I'll explain a little bit about how all that came about as we go. I'll turn right now to just developing sort of a background for this area of research. So quantum cognition does not posit that phenomena at the quantum level affect the brain. There are people who do posit this, and that endeavor is quite separate from what we're doing. It uses abstract formal structures originally developed for quantum mechanics. And so many branches of mathematics were developed for physics and then only later applied in other fields. So it's in that spirit that we are drawing upon the formalisms of quantum mechanics and applying them to cognition. So quantum mechanics resulted in a new theory of probabilistic and dynamic systems that is more general than classical theory. And some of the early work that led to this area of research, I guess very early speculations about the application of quantum theory to psychology go back to Bowman-Hiley in 1975 and in the 80s. We also see in the 80s the comparison of classical and quantum probability, macroscopic systems with non-classical probability calculus, and the notion of quantum structure. And Arts is actually my PhD supervisor. So my PhD supervisor was in the mathematics department, but his own PhD had been in physics. And how did I end up doing my PhD with someone who was basically a physicist? I was at an interdisciplinary center, and I was very familiar with the problems that psychologists were having describing how concepts combine. And this is a really important process because all of language depends on understanding what happens when concepts and words come together. And I had this sort of crazy kooky idea that you could model this using as an entangled state. And I met with Dirk Arts and I talked to him about it, and I ended up getting a fellowship to do my PhD with him that was worth more money than any postdoc in North America at the time. And so I was thrilled to go off and do this. And then when I actually got there, he didn't really think that it could be done. And so I spent my first 6 months there learning as much quantum mechanics as I could, and trying to convince him that this was actually a doable thing. And eventually he agreed. And at this point, there exists hundreds of papers trying to apply the formalisms of quantum mechanics to questions around concept combination and other areas of psychology. So in the 90s and early 2000s, you started hearing people talking about quantum-like structures and generalized quantum theory. And also in the 90s and early 2000s, you started seeing the application of quantum theory to decision-making, probability judgment errors, concept combination, and the influence of a context on a concept, as well as quantum game theory. And it is now quite an active area with many areas of application. So to decision-making in psychology and economics, probability judgment errors, game theory, semantic analysis, context and combinations of words and concepts, creativity, memory, information retrieval, and somewhat reluctantly humor. I put somewhat reluctantly there because I actually started talking with my supervisor, Dirk Arts, back in the 90s about applying these quantum formalisms to humor. And then it was 2016, 2017, and I happened to be talking to a colleague, Kirsty Keto, and saying, you know, this is just such a low-hanging fruit, it just has to be done. But I had kind of given up on this area of research. It become, I'd been in there at the ground level, but it become very technical, and it was a little bit peripheral to what I had started out wanting to study, which was how do we develop a general framework for in what sense culture evolves. And so I had sort of wanted to just stick with that. That seemed to be as interdisciplinary as anyone could expect. And I had sort of dropped out of developing these generalized quantum formalisms and applying them to cognition. But given that 20 years had gone by and still nobody had done this, applied it to humor, Kirsty and I decided to actually do a study of this. I had sort of been thinking, I don't know, leave that topic to smarter people and let them do it, but they hadn't done it, so we decided to give it a go. So what is the rationale for this project? Well, there are many sources of rationale for it, and I'm just going to give you some of the flavor of them. So psychology and cognitive science have always developed models that assume that judgments exist in definite states. Now, we may use stochastic models to analyze them because we don't know what the state is, but we assume that they actually just exist in definite states, and we just don't know what that state is. However, humans actually experience states that are indefinite. They may be ambiguous, they may be confused, they may allow for uncertainty. And so there may be states that have the potentiality for multiple ways of unfolding. There may be multiple possibilities for the potentiality in these states to be expressed. And quantum theory provides one way of dealing with this. So we can describe indefinite states as superposition states. Another piece of this rationale is that we don't retrieve items from memory, but we actually reconstruct them. And our retrieval will always be affected by the context and will always be affected by what we've experienced since we originally laid down that memory. So we reconstruct in a relevant, context-relevant manner. And quantum theory can describe the transition from an indefinite state to a decision or interpretation of some ambiguous situation as a collapse. In psychology, we also encounter order effects. So judgments can disturb each other. I'll give you a little example of this. So if I first ask about something very sad, and I ask the question, did that make you sad? So that's the first question that I ask you. And then I ask you the question, are you happy? You may be much less likely to say that you're happy after that first question. Whereas if I had asked those questions in the reverse order, you might have been quite likely to say that you are happy. So A sets up a context that alters the answer to B, whether it's true or false. So we cannot describe a joint probability of the answers to A and B. All we are able to do is to assign a probability to A then B or B then A. And incompatible judgments or questions can be described in the quantum theoretic approach as non-commutative measurements. Now, classical or cognitive science has always used classical probability, which assigns probabilities to events defined on sets. And it assumes unicity. So all events can be described by unions of elements of a sample space. So it assumes the axioms of Boolean logic, and this includes the distributive axiom, which gives rise to the law of total probability, which basically, I can give you an example of what that says. If you look at the little graph I have over here that says G stands for the proposition that Alice is good, and T stands for the proposition that Alice tells the truth, and F stands for the proposition that Alice tells falsehoods, then the law of probability, total probability says that the probability of her being good equals the probability that she's good times the probability that she's good given that she's truthful, plus the probability that she's good times the probability that she's good given that she tells falsehoods. So this is what cognitive science assumes, but we may entertain possibilities other than she's good and truthful or good and tells falsehoods. So Alice may be good and somewhat truthful or good and mostly truthful. So we experience violations of unicity. We can often not ascribe a joint probability to such unions. And we tend to require different sample spaces for different parts of a task. And this has been extensively studied in psychology. So you give people experiments, and you find that if there are many different parts, they can't think of all of these possibilities at once. They have to break it into subtasks. So this can be captured using axioms that assign probabilities to events defined as subspaces of a vector space. And this is exemplified by the conjunction fallacy and the disjunction fallacy of Kahneman and Tversky. So Kahneman actually won the Nobel Prize for this work. Tversky, I believe, had already died by that time, so he couldn't get the Nobel Prize. But basically, they gave participants in psychology experiments situations like the following. So Linda is 31 years old. She's very outspoken. She majored in philosophy. She cares deeply about social issues. She participated in anti-nuclear experiments. And then you have to give the probability that she is a feminist, the probability that she's a bank teller, the probability that she's a feminist and a bank teller, and the probability that she's a feminist or a bank teller. And so I've given you the probabilities that were given by the participants in this study. And these were undergraduate students at, I believe, Stanford University. And as you can see, there's something kind of strange about these probabilities. So obviously, the probability that Linda is a feminist and a bank teller would have to be greater than the probability that she's just a bank teller, and greater than the probability that she is just a feminist. But of course, as you can see, it's actually it would have to be less than the probability that she's a bank teller and less than the probability that she's a feminist, because of course it's more constrained. She has to be both of these things. But they actually gave a bigger probability to the fact that she's a feminist and a bank teller than the fact that she's a bank teller alone. And so that's an example of the conjunction fallacy. It also demonstrates the disjunction fallacy, because they say that the probability that Linda is a feminist or a bank teller is actually lower than the probability that she is a feminist alone. And it turns out that this seems illogical, but you can actually give this a quantum interpretation. And so this was done by my colleague Boesmeyers, Pothos, Franco, and Trueblood. And so they explained it as following. They say that you have two different basis functions. So you can, the pinkish line there, that's the state vector. And if you collapse it first with respect to the question of whether she's a feminist, well, that's represented by the blue axis there. And so that is quite likely. And so you take that line and project the pink line to the blue axis Fy, and then you project that onto the red axis, which represents whether or not she's a bank teller. And if you do that, you get 0.30, which is actually quite close to what they got in the experiment, 0.36 for Linda is a bank feminist and Linda is a bank teller. So that's one example of how these quantum cognition has applied a different quantum type approach to these kinds of paradoxes that were found in cognitive science. Another part of the rationale comes from findings of non-decomposability. So following initial probabilistic models of entanglement experiments, there's been a large literature on general probabilistic foundations of quantum correlations. Piron is actually the supervisor of my PhD supervisor. And it gets applied to systems that are non-decomposable, so that cannot be analyzed by considering their components separately and then synthesizing the results. And there's a growing, though somewhat speculative, literature on the application of entanglement to non-decomposable phenomena in cognitive science. So if I give you this conjunction of two words, apple chip, I could ask you, what do you think of? Well, you can actually study what answer people give to this, and there are different possible interpretations of apple chip. So I could prime the fruit interpretation. So apple chips that are similar to potato chips by showing you a banana. Or I could prime the apple chip made by the Apple company by showing you a picture of a circuit. And that's what has been done. People have done these kinds of experiments and tried to apply some of the methods of quantum that have been used in quantum mechanics to see if you can understand what is going on in the results that people give. So here we have on the left, we have the different interpretations of apple, either as a banana or as a computer. And you say +1 if it is interpreted as per the prime. So if you got the banana prime, you're more likely to interpret it as a fruit, but you're not always going to interpret it as a fruit, right? You might have somebody that works in electronics who still doesn't interpret it as a fruit. And if you don't, then you would interpret it using the more electronic interpretation. And similarly, chip can be primed using the potato interpretation or the circuit interpretation. And you can generalize this by asking, can we construct a joint probability distribution for all of the probabilities of A1, B1? So interpreting it in terms of the first possibility for the first variable and the second possibility for the second variable. Can we construct a pairwise joint probability distribution from the pairwise joint, can we construct a joint probability distribution, PR A1, A2, B1, B2, from the pairwise joint distributions of PR A1, B1, PR A1, B2, PR A2, B1, PR A2, B2, and it turns out that the answer is actually no. And there's a bunch of different papers on this. The first one was conducted by myself and my colleagues back in 2000, and it's called The Violation of Bell Inequalities in the Macro World. So you can check that out if you're interested. But other groups have looked at this as well, including Peter Bruce's group in Australia. And so I've been hinting a little bit at this point about concepts. And now I want to just tell you a little bit more about what concepts actually are. So we make sense of the world by classifying similar raw experiences. So raw experiences are sometimes called percepts as instances of a concept. So we learn at an early age that we can group all these different kinds of dogs, all these different instances of dogs that we encounter as members of the same concept, the concept dog. And psychology has come up with many different kinds of theories about what we're actually doing when we categorize things as instances of concepts. And so the oldest theory that goes back to Wittgenstein actually is referred to as the classical theory. And that's the idea that concepts have defining features, definite boundaries, and a fixed structure. And Eleanor Roche, who I did a postdoctoral fellowship with at Berkeley, came up with the idea that no, well, she came up with a whole bunch of different studies that showed empirically that concepts actually have blurry boundaries. They have they're context dependent, and they also exhibit something called graded typicality. That's the idea that one thing can be a better exemplar of a concept than something else. So for example, a robin is a better exemplar of the concept bird than, for example, rooster. And she gave people a whole bunch of questionnaires that actually provided her with data that the classical theory of concepts that had been assumed since the time of Aristotle was wrong. And she has great stories to tell about the process of trying to get these papers published. They were not able to be published for a long time. And after they were published, they suddenly got so much attention that she was overwhelmed. And so she came up with a new theory of concepts called the prototype theory of concepts. And that's the idea that we organize different exemplars in our memory and compare them to prototypes that are the most typical instances that we hold in our memory, or something that is actually not even a specific instance. It's nothing that we've ever actually experienced, but it's something that captures the essence of what it means to be, for example, a dog. And then people also came up with challenges to the prototype theory, such as the exemplar theory, which is closely associated with Rob Noskoski at Indiana University, which is the idea that concepts actually exist as collections of the most salient instances that we've ever encountered of that concept. Probably, so for example, for the concept dog, we might have the 5 to 7 most salient instances we encountered of dogs at a young age, and those would form the basis of our concept of what it means to be a dog. And these, or especially the last two theories, were actually very successful at predicting how people would decide if something is a member of a single concept. But all bets were off when it came to seeing how they dealt with combinations of concepts. When we started examining how they deal with combinations of concepts, it was very difficult to come up with a formal theory of concepts that obeyed what people actually did in the lab. So no theory of concepts actually modeled how people handle combinations of concepts. Concept combinations are often non-decomposable. They violate the principle of compositionality. It was found that conceptual negation does not satisfy the rules of classical Boolean logic. People will say that X is tall and X is not tall is true if X is somewhat tall. So for these borderline cases, they would say that this completely illogical statement is actually correct. You also find overextension and underextension of properties of concepts and of exemplars or instances of concepts. And we found that concepts exhibit emergent properties, that properties that are not true of the instances, but they are true of the concept combination. Or you can have the disappearance of seemingly defining properties. So I like to use the conjunction kitchen island, because if there ever was a defining feature of any concept, it would be that surrounded by water is a defining feature of island. But if you have a kitchen island, Lord help you if your kitchen island is surrounded by water, right? You're in trouble. So a kitchen island is not surrounded by water. So a seemingly even defining property can disappear in the context kitchen. And this overall effect came to be known as the guppy effect, or the pet fish problem, due to a famous paper by Osherson and Smith. So they say that the guppy effect occurs when something is more typical of concept combination than it is of either concept alone. So for historical reasons, I'll just spell that out. They gave people examples such as guppy, and they found that guppy is rated as less typical of either pet or fish than it is of pet fish. So we get overextension of the exemplar guppy in the conjunction pet fish. And the question then became, how might we mathematically describe what a concept is in a way that's compatible with how they interact in our minds, in a way that's compatible with what we actually do when we're using concepts? And to reiterate, this is a really important question, because whenever we communicate with each other, whenever we read passages, we're using combinations in combination with other, we are using concepts and words in combination with other concepts and words. So Fodor, who is a famous philosopher of cognitive science, famously said, this is the most important challenge to cognitive science. So my supervisor and I came up with what we thought might be a new theory of concepts that might start to provide a quantum type solution to this question of how you define what a concept is. So it shifts this perspective from a concept as a container that holds its instances to a concept as an entity that exists in a state that changes under the influence of a context, where the context is playing the role that a measurement does in quantum mechanics. And a key concept in the state context probability theory, which we sometimes refer to as SCOP, is the notion of a ground state. So this state was never thought before. What is the state of a concept when you're not thinking? Nobody had ever actually asked that question before. But it seems to me that it's important, in order to capture the potentiality of concepts, to have even seemingly irrelevant instances and seemingly irrelevant properties be classified as relevant to the state of a concept. You have to think about the state of potentiality it's in when you're not thinking about it. And then you're thinking about the different possible situations in which it might become relevant, the different possible contexts in which it might become elicited as actualizing some of that potentiality. And so the ground state is the state that that the concept is in when you're not thinking about it. So it's a state of full potentiality before the potentiality is actualized by a particular context. So it's a really different way of thinking about what a concept is from how they'd been thought about before. So for example, you might have two concepts. You might have a concept A, which is fruit, and a concept B, which is vegetable, and concepts can exist in different states or possible instances, such as apple is an instance of fruit and carrot is an instance of vegetable. And these may have different properties, such as green or has seeds. And contests fall under the influence of context, situations that evoke these states. So pie might evoke apple, or lasagna might evoke carrot. And we can take the membership weights of properties and instances for a concept, or for a conjunction of concepts, or for a disjunction of concepts. And you might be wondering, okay, but where does the quantum aspect come in? And so I'll tell you a bunch of different ways in which SCOP and its offspring, and sort of other theories that have come around since SCOP have been incorporated into this formalism. So states of indecision has been represented as superposition states. And so you can have the one state and another state, and they both have different amplitudes, and they're both elements of a Hilbert space. And if you square these amplitudes, they add up to 1. So that's just renormalization. And I'm going to be actually elaborating on these afterwards. So I'll just go through them kind of quickly now. A judgment, or bringing a concept to mind in some context, can be thought of or modeled as a quantum measurement. You can have entanglement in concept combinations. You do that using the tensor product. You can have abstract concepts that may exhibit quantum indistinguishability. And I could go, this is actually new work that was done by a new PhD student of Didactic Arts. And I'll go into that. It's a little bit strange if we have time later on, but it's intriguing work. And yeah, I'll leave it at that for now. You can also have the inability to simultaneously assess with respect to incompatible criteria as quantum uncertainty. So for example, you might have two questions that it's really hard to think about them at the same time. And so they are going to have some kind of uncertainty relationship between them. You can't think about one question the same as the other question. And so they can be modeled as being incompatible. And you can also have interference in concept combinations and in judgments. And I'll show you some examples of this on the coming slides. Okay, so this is a schematic illustration of conceptual collapse under the influence of a concept. So say you have the concept diamond, and it has different properties. So some of these properties are that it symbolizes love, it sparkles, it's sharp, and sharp is not the most typical property of a diamond, but in the context of cutting glass, it's the relevant one. So this orange globe represents the full potentiality of the concept diamond, and we have context-driven collapse. And in the context of wanting to cut glass, the one that is most relevant is that it is sharp. And so these other properties just don't come to mind in that context. Okay, so now I'm going to give you an example of a study that we carried out that showed conceptual interference. And it was actually based on a much earlier example by James Hampton in 1988, where he had an experiment in which 40 participants were asked to estimate the degree of membership of 24 exemplars with respect to 3 different categories. So the exemplars were almond, acorn, pecan, peanut, olive, and so forth. So all of the items listed here and shown below. And so first they had to estimate the degree of membership of each of these exemplars that were randomly ordered with respect to the category fruit. Then they had to give the degree of membership with respect to the category vegetable. And then they had to give the degree of membership with respect to the disjunction of these, fruit or vegetable. And so this is sort of analogous to a double slit experiment. So what we found was we were able to get the degree to which each of these were listed as instances of fruit, first of all, and this was plotted on a diagram as follows, and there's a lot of technicalities in how that was plotted, but basically the one that was most typical of fruit was apple, not surprisingly, number 8, and the distance from apple shows the degree to which they thought that that instance qualifies as a member of fruit. So 7 was quite close to 8, and 7 is elderberry, so that rated very highly as a member of the category fruit, whereas some of these ones over the periphery, 13, 14, 15, 16, 21, 22, 23, 24. So those are things like broccoli, rice, parsley, black pepper. They were rated as very poor instances of fruit. And we did the same thing with vegetable. And the most prototypical example of vegetable turned out to be broccoli, number 21. And so the distance that they are from broccoli shows the degree to which they were categorized as a member of the category vegetable. So you can see 1 and 2, almond and acorn, were the instances that were least likely to be categorized as an instance of a vegetable, whereas things like 15, 16, and 22 were categorized as pretty good instances of a vegetable. And so what a classical theory would predict is that things that either categorized very well as an instance of a fruit or categorized very well as an instance of a vegetable would be categorized as an instance of fruit or vegetable. And also things like tomato and pumpkin, which did pretty well as a fruit and pretty well as a vegetable, might be expected to classify very strongly as a member of the category fruit or vegetable. But that isn't what the data showed. And so we applied a quantum model to this data. So we obtained the average degree of membership for each of K exemplars with respect to each category for all the participants. And then we gave something called the membership collapse probabilities, estimated by renormalizing, and this gives 3 times 24 values in the interval 0 to 1 that sum to 1. And then we gave them a Hilbert space representation. So the questions asked of the participants played the role of the measurements, and they were represented by orthogonal projection operators MK for each of the K exemplars. And fruits and vegetables are represented by orthogonal unit vectors A and B, and fruits or vegetables is represented in the Hilbert space by the superposition of 1 over root 2 times A plus B, and then we have the probability that it is categorized K as either fruit or vegetable, and the probability that is categorized as either fruit or vegetable. And then the last term there is the degree of interference. So it's what differentiates this model from a classical model. And what we got was actually something that looks very similar to the pattern of light passing through an elastic material under stress. So it looks to be an interference pattern. And that is just one of a whole bunch of suggestive results that suggest that quantum theory can actually be applied to cognition. All right, so now I'll turn to the quantum theory of humor, which I developed with my colleague Kirsty Keto, who is featured here. And it's a new direction, so we use the quantum formalism to model cognitive process of getting a joke. And so to explain this, I'll have to tell you a little bit about humor itself. So humor involves ambiguity, words or situations that can be interpreted different ways, and involves a change in meaning, often from a more tendentious or lewd to a more innocent meaning as a new perspective is introduced or new contextual information becomes available. And this is referred to as bisociation. So the coming together of different meanings or different ambiguous interpretations of some word or stimulus or image. And because there is so much ambiguity in humor, it seemed like a really promising candidate for a quantum description. And so I'll tell you a little bit about how it might be applied to first nonverbal humor. So here we have dog in the context of cute, and we experience that as not scary. So if we have dog represented by that state vector and it collapses to the x-axis, not scary. And we could have dog in the context of angry, and that would be experienced as scary. And we could also have a bisociation, which is perhaps modeled as a superposition of two possibilities. One, that it is cute, which is usually not scary, and the other one that is angry, which is usually scary. And in this situation, because of these two possibilities being experienced at the same time, we might experience that as being funny. So how would this apply to verbal humor? So to see how the quantum theory of humor was tested, consider the joke, time flies like an arrow, fruit flies like a banana. The humor hangs on the ambiguity of the words flies and like. So the first frame, F1, the setup, primes the listener, so I told you earlier what priming is, to collapse upon interpreting flies as a verb and like as a preposition. And then the second frame, F2, the punchline, primes the listener to hover between that first interpretation and a new interpretation, fruit flies as a noun and like as a verb. And so how would you represent this as in the quantum formalism? So you've got the state vector is a superposition of the different states that flies could collapse to. And that's vector P there. And in the setup shown in black, it is likely to collapse to the vector W, which represents its meaning as a verb. And that's shown by the fact that the subspace A1 is greater than the subspace A0. But under the influence of the context fruit, shown in green, flies is represented by the state vector PE, and it collapses to the orthogonal projection vector UE, which represents its meaning as the noun fruit flies, as shown by the fact that PO is greater than P1. And so we have these two possibilities, that it's interpreted using the first of the two possible interpretations, or that's interpreted using the second of the two possible interpretations. And we can have some probability of each of these two different possibilities for each of the two words, fruit and flies. And so we carried out an exploratory study to see if this actually made any sense. And so the goal of this was to assess the appropriateness of a quantum approach to the study of humor. And we used 85 first-year undergraduate students who enrolled in an introductory psychology course. And we asked the participants to we were given the participants were given a questionnaire consisting of 35 jokes and joke variants in a randomized order. And then they were asked to rate the funniness of each using a Likert scale, which is just a scale, in this case, from 1 to 5, where 1 represents something is not funny at all. And 5, we said to only answer 5 if it is fall off the chair hilarious. And given that they actually didn't find our instances of humor very funny, I kind of, in retrospect, wish that we had just said 1 is not funny and 5 is funny, because they actually ranked them all kind of low. But, you know, you learn from your experience. So the stimuli for each of the 35 jokes, we developed a set of joke variants. So VO is the original joke. So for example, time flies like an arrow, fruit flies like a banana. VS is the setup only, so time flies like an arrow. VP is the punchline only, fruit flies like a banana. Now in the experiment that I'm going to tell you about, we actually didn't use the other ones, but I'll tell you about them anyways because they're sort of fun. In the CP variant, so that's the congruent punchline variant, it's the original setup followed by a congruent version of the punchline. So time flies like an arrow, fruit flies like a bird. In the CS variant, so the congruent setup variant, it's the congruent version of the setup followed by the original punchline. And an example of this was horses like carrots, fruit flies like a banana. In the IS variant, we have the original setup followed by an incongruent version of the punchline. So for example, if VO was why was 6 afraid of 7? Because 7, 8, 9. And IS variant was why was 6 afraid of 7? Because 7 was a 6 offender. And so our hypothesis was, if the quantum theory of humor is correct, jokes violate the law of total probability. So funniness should satisfy the distributive axiom. That's that the total probability of the observable equals the sum of the probabilities of it under each specific condition. So we had two observables. First, a funniness observable with eigenstates 1 or 0, and a semantic observable, which represents the 2 possible meanings of the ambiguous word. And if the system satisfies the law of total probability, then the probability that the joke is judged as funny equals the sum of the probability it is judged as funny for each possible meaning or interpretation according to this equation. And if it does not, then we have evidence that the law of total probability is violated and that a quantum approach to humor might be appropriate. And so we had a bunch of values that we obtained by summing over all of the participants for all of the possible jokes and their variants. And a first result to note is that it does support the general idea that incongruity is actually funny. So you can see here that, as I was saying, none of them was rated as particularly funny, but the ones that were the funniest were the ones that involved incongruity. So the original joke or the incongruent setup or the incongruent punchline. But do the results support the hypothesis that jokes violate the law of total probability? And so we analyzed each of the possible 35 jokes, and we showed here how funny they are with respect to the original joke, the setup, the punchline, and then also we obtained the funniness for the mean of the setup and the punchline. And so we obtained the frequency with which each joke and each joke variant was considered funny, setting our confidence intervals at 95%. So those black bars represent the confidence intervals. And since the pun was not considered very funny, for the funniness threshold, we used a pretty low value of 2.5. And this, the idea that puns are not considered very funny comes from past research, but it's also what we found in this study. Now, we had a challenge And that was the following. So to test for the violation of the law of total probability, we would need to construct expressions such as the following. The probability that's funny equals the probability of 8 plus the probability that's funny given it's interpreted as 8 plus the probability of AT. So the last ones were 8, the number, plus the probability that's interpreted as ATE, as in to eat, plus the probability that it's funny given that it's interpreted in terms of the eating meaning, so ATE. And we have the probability the whole joke is funny, and we have the probability that the setup alone is funny, and we have the probability that the punchline alone is funny. And so these are indicated by the green boxes above. But we didn't have the probability that EYT is interpreted as the number 8, and we don't have the probability that EYT is interpreted as ATE in the second instance. So we couldn't actually calculate what we needed to calculate, although it does seem pretty reasonable that to assume that the participants use the context to interpret EYT as 8 and as the number 8 in the setup, and then they interpret it as ATE as intended. We don't know for certain. To know for certain, we would have to have some kind of setup which would probe how they were interpreting this ambiguous verb without interfering with their actual appreciation for the joke. And we weren't able to do that. But because the results were so extreme, so the original joke was just so much funnier than the setup and the punchline, what we did instead was we asked the question, is there any way that the semantic probabilities could have possible values that would satisfy LTP, the law of total probability? And so examination of the graphs of the 35 jokes and their variants suggests that there is no way to choose semantic probabilities that would satisfy the law of total probability. So our results suggest that the law of total probability is in fact violated, and that we have preliminary evidence for a quantum theory of humor. And this adds to the accumulating evidence that the generalized quantum formalisms are needed to capture the contextual nature of cognition. And I actually wasn't even sure if this paper would get accepted or not, given that it was a little bit weird, and we weren't quite able to prove that it was violated. So I was somewhat stunned when it was actually one of the actually is probably the thing that I've done that got more attention than anything else I've ever done in my academic career. And so that paper has more than 30,000 hits, and I got phone calls and contacts from all over the world, and there were actually hundreds of little papers written up about this silly little paper, which is, I don't know, it's a little bit sad after doing just so much more work on other things, and this silly little study getting all this attention. But anyways, it does add to the accumulating evidence that quantum formalisms are needed to capture the contextual nature of cognition. So some brief conclusions: cognitive sciences encountered situations that are reminiscent of the situations faced in physics a century ago. We have indefinite states, non-classical probabilities, non-decomposability, etc., and perhaps some of the mathematical structures developed by physicists to address such situations are applicable in cognitive science. And I thought I would take this opportunity to tell you, if you're interested in this, might want to explore it. There's actually a quantum social science boot camp, July 12th to 16th, organized by Ohio State University, funded by the Carnegie Corporation of New York. And you can check that out. And thank you for listening. And I just wanted to tell you that many people have contributed to this research program, including all of the following. And that's it. I welcome any questions you might have.
Great. Thanks very much, Liane.